Since the two-piece clock body is a large print, I've created a cut of the two mating sections to be used as a test piece to ensure a successful print. This is in an effort to prevent a big wasted print body if adjustments were necessary. In my case, I print these to 60% scale, and the two halves slid together quite well. My thought is that if it works at a smaller scale, when the tolerances are also reduced, then it should work at the larger full-size scale intended for this build. For a good fitment of the drive gear onto the stepper motor shaft, it may be necessary to slightly adjust the scale of the drive gear print. The goal is to reduce or eliminate any play with the stepper motor shaft. My preference is for a snug fit, where the gear needs to be lightly pressed onto the motor shaft. The play you see here is from the motor's internal gears, so not much you can do about that. In addition, there's an opportunity to compensate for any play in the code. I'll review that in the code section of this video. Here's something I did not go into too much detail on in the previous Part 1 video. In addition to the viewing window for the gear meshing, I've also added another window for viewing and access to the limit switch spring. Here you can use a small screwdriver to manually push the spring and test that it's making contact and actuating the limit switch. In addition, I recommend first installing the backplate with the limit switch installed, but with the drive gear removed. Rotate cam D1 and observe that when the limit switch boss or peg on the driven gear engages the limit switch spring, it actuates the limit switch correctly. I first recommend installing at least 2 opposite corner screws. That way the backplate is in a secured position when testing the function of the limit switch. Not sure if that click is being heard on camera, but it clicks about right there. If it appears to be functioning correctly, you should be good to move on. This point of contact between the switch, spring, and driven gear will probably vary a bit between different builds of this clock. For that reason, I've added fine-tuning parameters to the code that will allow you to, well, fine-tune each digit to achieve optimal function and display. This fine-tuning will be discussed in the code overview section of this video.
Alright, here is the code that I have written to control this clock. I'm not a professional coder or programmer by any means, so I imagine there's probably room for improvement or increases in efficiency or more shorthand ways of achieving these functions or computations. I enjoy learning, so if you do see any significant improvement opportunities, please let me know. My style and/or form all stems from a couple of C++ classes I took years ago. Alright, to the code. It consists of 5 functions plus the loop that compute the time based on the data from the RTC and control the movement of the motors. I've included an explanation of each function here at the beginning of the body of the text. In addition to the main body of code, I'm using 2 additional libraries. One for the stepper motor control and the other for RTC communication. Please refer to the credits I've provided in the description for recognition of the creators or the source where I obtained these libraries. In addition, I've added comments to many lines within the code to explain what is going on and/or why it's there. There are 2 locations in this code that will require your input. The first will be setting the RTC to your desired time. The second will be the fine-tuning parameters of the stepper motors for each digit that I mentioned earlier. So first we'll go to setting the time. Setting the time is achieved by uncommenting this line and entering the desired or current time into the argument sections within the parentheses separated by commas. The first being hours, minutes, and then seconds. The RTC library requires the time to be entered in a 24-hour format. The other 2 lines aren't really relevant to this particular application or project, since this is just a clock and there's no means to display the date or day of week. So you can leave these alone if you want. So once entered, flash the code to the Arduino and then recomment the function and flash one more time. If your final flash isn't done with a commented time set function, the code will set the clock to the entered or desired time every time it's powered up. The second user input will be the fine-tuning parameters. So in addition to the variables used in the code, there are also many physical variables that will alter the experience from person to person, including 3D printer settings, material, hardware, and electrical components. For this reason, I've added 3 tuning parameters that can and should be adjusted for optimum precision of each of the motors. These values represent the quantity of steps each motor will move relative to the point at which the switch is actuated. Here's a basic rundown of a motor's homing operation. Let's say the clock has just been powered up. The Arduino has no idea what the rotational position is for each motor. So, the motor begins a blind forward rotation, continuing until the limit switch is actuated. The motor will then rotate an additional tuned amount to position the driven gear into the correct alignment with the digit intervals of the cams, resulting in properly displayed digits, i.e. no in-betweens or partially showing segments. The ones and hours digits should have the same or similar value since these digits have a 10-digit display range. The tens will be different in both magnitudes and sign because the minute tens digit only has a range of 6 numbers, but uses the same driven gear as the other 2 digits. So its limit switch actuation point falls in between the 0 and 5, meaning the motor needs to rotate in reverse considerably more to get back to the 6th interval, or the number 5, i.e. the home digit. So why didn't I just make a driven gear specific to the minute tens place digit with a limit switch boss or peg that aligns with the number 5 position? Many reasons. It would have changed the angle and position of the limit switch install, which would not have fit in the available space. This would have required a new backplate, midplate, driven gear, and potentially a new limit switch spring. I concluded that it's far more preferable to keep the printed components uniform and instead compensate for this difference in the code. To actually determine the correct tuning parameters, I like to use the time 7:57 as a visual gauge. I have found that the number 7 is a great representative for a good tune. Basically, if the number 7 looks good, then so will all the other digits. And more specifically, when tuning the number 7, I like to keep an eye on the D segment and tune the home position to the D cam's valley, i.e. the D segment is at its lowest point between the 6 and 8 digits.
Alright, so enough explanation, let me just show you an example. Ideally, you just keep the tuned values as I've pre-entered them and everything will look good on your end. However, I think there's a good chance you'll need to make some adjustments. So the first thing I like to do is set the time to 9:59 for the first power up. This is the home position for each of the digits. So setting to 9:59. And then I'll plug it in. And the digits will home themselves and set the time to 9:59. I'll disconnect the power to keep that time displayed so it doesn't advance any further. Once the homing and initial time setting functions have executed, observe the displays. Look for any partially showing segments. If everything looks good, you're good to go. However, if either of the 10 position digits are too advanced from the optimal display, you'll need to reduce that tuned value for those digits. Likewise, if either is short of the optimal display, you'll need to increase that tuned position value. Similarly, if the 6th position digit, i.e. the minutes tens place, is too advanced from an optimal display, the tuned value will need to be reduced, i.e. make more negative. Likewise, if it's short of the optimal display, the tune value will need to be increased, i.e. make less negative. Once I'm satisfied with the results for a 9:59 display, I'll then set the clock to 7:57 since the number 7 could still expose need for further calibration. Then I'll observe. Setting the time here to 7:57. I'll flash this to the Arduino. And then once that's complete, I'll power up. And again, I'll remove power so that it stays here. And I'll just look at the segments once more, making sure nothing is exposing itself here. So maybe a little adjustment there with the 7 on the hours, just a little bit. Okay, I'm going to quickly show an example here of a digit that needs its tune value adjusted. So I'm going to intentionally set a value that I know is going to put it off from the preferred location. So I'm going to change the tune 1's parameter from 180 to 300 and set the time back to a 9:59, mainly just for this minutes ones place, and you'll see that a 9 is not going to be displayed. All right, so once that's loaded, plug the power back in and observe how the 9 homes itself. Okay, so you can see how the center segment is falling. This segment here is partially showing. So here's an example of what, when your first power up, could look like, hence why you need to adjust the tune values. So if I put it back to 180, the value that I determined for that particular digit, in my case being the optimal tune, and there it displays a clean, desirable 9. Okay, so the last step I like to perform for the calibration is to power up the clock under 2 different conditions. The first, the limit switches are engaged upon power up, and second, the limit switches are not engaged at power up. So for the first condition, I've set the time back to 9:59, so all 3 limit switches are engaged. I'll then disconnect the external power source and keep only the USB connected to prevent the motors from rotating immediately after I flash the code. So I'll then set the time to 7:47, so none of the switches are engaged, and then flash that code. All right, so after that's complete, I'll plug this back in, and we'll see how the 747 is displayed in the first condition where it started with all 3 limit switches engaged. I'll again unplug that so that it holds that and not change to the next minute. So if the 747 display is satisfactory, I'll move on to the second condition. So here I'll make sure to start with a time where none of the displays are showing their home digit. As showing right now, none of these are in their home position. So I'll just leave the set time at 7:47. So I'll plug back in the external power supply, but first I'll send the code one more time so that it resets the Arduino. Once that's complete, I will then plug the power source back in and let it reset itself back to 7:47. All right, well, you saw there, it changed to an 8 before I could unplug it. That's just because the homing and setting took longer than a minute, so by the time it was complete, the minute had updated. But I think everything looks good, so I am satisfied with then the second condition. And now for the final test, I like to observe the time change from 12:59 to 1 o'clock. This is because the operation from 12:59 to 1 o'clock includes the most complex motor sequence, plus it uses the hour carry cam. So I'll set the time to 12:59, flash the code. So setting the time in here, 12:59. I'll flash the code, wait for that to finish, plug back in the power, let it set itself to 12:59, and then wait for it to change to 1 o'clock and observe that, making sure everything looks good. All right, well, as you can see, this segment right here didn't quite close all the way, so that tells me that there will need to be one final small adjustment to this. But ultimately, as you can see, Testing this in multiple conditions helps you to ensure that you have the right tune values for every digit. So that's sort of where I guess the trial and error, or if you want to call it the fun part, comes in of calibrating your clock. So once you're satisfied with that, I would say that it's probably ready for service. You may notice that IO pin number 5 is unused but called out in the code as commented lines of text. This is because I plan to roll out an update that includes a button used for setting the time in an effort to make the clock more user-friendly and not require a flashing of the code every time the time needs set or updated. Otherwise, hopefully this video is helpful. I try to incorporate the things that I experienced upon testing and prototyping that I think are important to understand. As always, please let me know if you see any major flaws or issues with my procedure. Thank you.